Welcome. In this video, we're going to continue our discussion of logarithmic equations. Let's start by considering the equation y equals log base 2 of x. We can choose a value of x to substitute into the equation and find the resulting value of y. For example, with x equals 8, we have y equals log base 2 of 8. This is equal to 3. Now, let's verify, because we can also verify that this is the case by writing it in the equivalent exponential form. Log base 2 of 8 equals 3 can be written as 2 cubed equals 8, since 2 times 2 times 2 is equal to 8. Now let's try this with a negative value of x. Say x equals negative 8. Then y equals log base 2 of negative 8, which equals, let's figure this out. We can use the equivalent exponential form to better understand this. Y equals log base 2 of negative 8 is equivalent to 2 to the y equals negative 8. Now on your own paper, multiply 2 by itself a few times. So here's 2 times 2 is 4, and continue that and see what you get. And that might help you answer this question. That is, what is the y here? All right, by now you should have tried a few values, and you should have noticed that no matter how many times you multiply 2 by itself, you'll always get a positive number. So to answer question 1, why is there no value of y equals log base 2 of x when we choose x to be a negative number? That is because no matter how many times we multiply a positive number to itself, the number will always be positive, and that is the resulting number will always be positive. Now for number 2 and 3, I'm going to suggest that you answer these together. So please take a moment and pull out GeoGebra. I'm not going to show how to use it since there's been ample tutorials on using GeoGebra on the Canvas page up to this point. So look into question 2 and 3 and use a table of values to answer both. So please pause this video, use GeoGebra to create this table for 3, and then I suggest using this table to answer your question for part 2. Okay, now that you've paused your video, you should have a table filled in. And here's what I have filled in from GeoGebra, and these are the 3 points I really am concerned with and want to discuss. In GeoGebra, we get question marks here. That means that our function is actually not defined for these values. So we can't put in an input of -1 since we won't get an output. Next, let's look at this one. For 0, it says negative infinity, but in reality, as you notice, this one should also be a question mark, since as we're approaching 0, I can sketch a little mini graph here. There, it's a good spot for a mini graph. As we're approaching 0, from the x-axis, y is just getting smaller and smaller, never actually touching the y-axis. And you can see that by looking around on the graph. So all these question marks really mean undefined. This function is undefined at these values. This shows that for each positive value of x, we have one value of y. Thus, y equals log base 2 of x is a function, and we can write f of x equals log base 2 of x. Similarly, for each base value, that is for each b greater than 0, y equals log base b of x is a function where each positive value of x gives only one value of y. Now, although log functions are only defined for positive x values, so they're only defined in this direction, so numbers larger than 0, the above table shows that the y values, can be positive, negative, or 0. The graph of f of x equals log base 2 of x is shown to the right, not the left. Let's use this graph to verify the solution, that is the value of f of 2 we found in question 3 on the previous page. So this graph here is f of x, and here is the line x equals 2. To evaluate f of 2, we just need to look at where this graph for f of x intersects this dotted vertical line. That occurs here at 1, which tells me f of 2 equals 1. This confirms what we found on the previous page. Part B, let's use the graph to verify the value of f of 0.5 we found on question 3 on the previous page. So here is 1. So 0.5 is about here. I want to know where this dotted line again intersects f of x, and that occurs right about here, and that's at -1. That tells me that f of 0.5 is equal to -1, which again confirms what we had on the previous page. So for part C, before we use this graph to explain why f of -1 is undefined, let's recap what we did for part A and for part B. For each of these, this value inside our function notation, we looked at where the vertical line intersected our graph. And that intersection point was the answer we were looking for. So in this case, it was 1 for part A and -1 for part B. So where is -1? -1 is here. And now, does this vertical line ever intersect this graph of f of x? It does not. That tells me that f of -1 is undefined, since there is no place where these two graphs or these two lines will meet. Next, let's use the graph in part D, or for part D, to estimate a solution to f of x equals 3.5. Now this is a little differently. Here, when the number was inside the parentheses, say for 2, we looked at where this vertical line intersected our graph. Now we notice that inside my parentheses is an x. So we don't know what the x value is, but we know what the y value is. The y value is 3.5. So we're looking at where this horizontal dotted line intersects our graph of f of x. And that looks like it occurs somewhere past 11, so a little bit above 11. I'd guess about 11.25 would be my guess. So x is approximately 11.25 or 11.3, somewhere around there. I mean, honestly, I'd probably even accept an answer of like 11.2, anywhere in that general range. Part E, let's use technology to reproduce the graph of f of x equals log base 2 of x and use it to find a precise solution to f of x equals 3.5 to 4 decimal places. So now on my screen you can see GeoGebra this time, and I'm going to rearrange so that I can see this intersection better. And if I tap it, I can see that I'm at 11.3137 to 4 decimal places, which jives pretty closely to what we estimated here by using the original graph on our handouts. Finally, there is some reading that you should review independently on the class discussion page. Problem 5. By now you should have read the bottom of the previous page independently, and recall that if you see log without a base, you assume that's a 10 there, and that the natural log of x is actually log base e of x. All right, so now let's solve these part A and part B only. Part C and D are independent work, and let's find an exact solution without technology and then use technology to find an approximate solution. So let's start by finding an exact solution to both first, and then we can use technology. So first, let's solve this all algebraically. So I'm going to pretend this is one big x here, and I'm solving 6x plus 3 equals 12. If I were solving this, my first step would be to subtract 3 from both sides. So that's precisely what I'm going to do here. Minus 3 to get 6 times log of x over 2 equals 9. Next, we need to divide by 6 to get log of x divided by 2 is equal to 3 over 2. Now comes the point where we rewrite this, and again, I'm going to emphasize this in red. This is like having a 10 there. So what we're doing is we're saying 10 to the 3/2 power equals x over 2. And now finally, to finish solving for x, let's multiply both sides by 2. And I'm running out of space, so I'm just going to show that this is x equals 2 times 10 to the 3/2 power. And that can be moved actually to here. Let me copy and paste this. And there is our exact solution. Let's do the same thing for part B. Now for part B, let's start by adding a 1 to both sides, which yields -4 times ln of x plus 8 equals -5. And now dividing both sides by -4, we have ln of x plus 8, and I dropped a negative here, excuse me, equals 5/4. Now, again, remembering that this is the net, a base of e. So I'll emphasize this in red by rewriting. This is the same thing as log base e of x plus 8 equals 5/4. We can rewrite this as e to the 5/4 power equals x plus 8. And now all that's left to do is subtract 8 from both sides. And we end up with x equals e to the 5/4 power minus 8. And this is our exact solution here. Now go ahead and open up GeoGebra. And as you can see, I have a blank GeoGebra screen up. And we can do this two ways to verify our solution. First, let's start by just typing in these values and getting a solution, but just like as if this were not a graphing calculator. So I'm going to type in 2 times, and then in parentheses, 10 exponent, 3 halves, so 3 divided by 2 power. And we're going to round to 4 decimal places. And we can actually get GeoGebra to do this. So I'm touching the settings in the top right corner, general, and rounding right now is to 13 decimal places. So let me switch that to 4, and I'm done. So now I don't have to worry about making a rounding mistake. So I have 63.2456. Okay, so what's a second way to do this? Well, a second way is to write down this as one equation, y equals this and y equals this, and find that intersection point. So I'm going to type in y equals 6 times log base 10. Again, when we don't see anything written down, we assume that's a 10 there. And then inside the parentheses, x divided by 2. And then I'm also going to write down y equals 12. And I'm going to stop here a minute. I missed something. I only wrote this part down under my first equation. I need to make sure to add that 3. So I can quickly go back and type plus 3. No harm, no foul. It is all fixed. And now hiding that, I have the left side of the equation here in green and the right side in red. And so let's move our image around on GeoGebra. And we can see that the intersection point matches what we figured out algebraically. Okay, so now let's try this for part B. So go back to the calculator mode. And let's just delete. And let's go ahead and type in e to the 5 divided by 4 power, then arrow over, minus 8. And what does that give us? It is negative 4.5097. So now let's do the same thing again. I'm going to type in y, not pi, y equals negative 4 times, and now under my functions, I'm going to type in ln, and then inside x plus 8, finally subtract 1. And that's in red. So this entire left-hand side here is in red. And then I'm also going to type in y equals negative 6. And that's in purple. So this entire right-hand side is in purple. Let's hide that. And my intersection is right here. And if I tap that, I get the same answer that we figured out algebraically. Please continue parts C and D independently. I hope this video was helpful.